This has been the week of Bertram. For those of you unfamiliar, the HRI reading group went through his paper on Monday. He gave a talk to, was that a philosophy talk technically?
So Tuesday was social and decision sciences, Thursday was philosophy.
Or was that billed as something else? Was that like the AI?
It was philosophy.
Philosophy, okay.
Ethics.
Ethics, okay. Today's robotics. I'd like to thank you all for coming on a morning, on a Friday, which is a little cold and gloomy. I appreciate it. For those of you not familiar with Bertram's work, he's been around HRI for a long time now. Were you the
Not that long. If 4 to 5 years is long.
Okay.
I've done stuff that fits it, but
4 to 5 is almost half the duration of the conferences. So.
Yeah, that's right.
And so he's done some really cool work related to how people interact with robots. And today he's going to talk about appearances, and I'll let him take it away.
Thank you, Aaron. Well, thanks for coming. I know there are 3 talks today, and what people typically tell instructors is not to announce to students that they're going to videotape the lectures, because then the students say, oh, okay, then I don't have to come to the lecture. So hello to those who are watching this now. If I induce a little guilt, then I think that's probably the right way to go. Sorry for the voice. I caught a bug, maybe a Pittsburgh bug, but at least I think I'm going to last for an hour here. And I want to tell you about some work that's not yet published. The first part is, the second part we're working on right now, that is surprising or has been surprising to me. The starting point was straightforward and, oh, these are good data, these are good results. And towards the end it was more like, is that possible? That seems impossible. Let me reanalyze the data. So we'll see whether you're surprised too, and whether we'll learn something about an old topic in HRI. What the appearance of a robot does to the human interactant initially, over the long run. This is all initial stuff. In the long run, we don't know what happens. There are very few longitudinal studies in HRI, and I'm another one who first looks at the initial phase, but you'll see that there are at least a few interesting lessons to learn from that. So this is the team. For those of you who were here yesterday, know that my thing here, that my remote has to be replaced because it's very eager to go to the next slide, more than I am. So I have to learn to very lightly touch. So this is the team of researchers who contributed to this topic. Beth was a postdoc at the time we did the work. Sven was a PhD student and then postdoc. And Danny Ullman is still a PhD student with me. He's the one who's working on trust and the trust scale. So I could have a bigger box. There is a ton of work on robot appearances, and it's really a core concern in HRI because there's so many potential decisions during the design phase and so many potential psychological layers of impact. And what some of this work has shown really is that a robot's appearance affects intelligence, sociability, likability judgments, credibility, submissiveness, obedience, and many other things. It also activates some social cognitive mechanisms that might be sort of more deep-seated, that are not judgments, but that in a sense happen. And we did a little bit of work on that where we presented an ambiguous figure on a table to participants, and it's a very short experiment. They basically say, okay, you'll get a question on the next page, please answer the question. And then comes on this picture either of a human or a robot or a cat or a piece of machinery, and the number in front of the agent or thing, and the only question that people get is, what's the number on the table? And what we found systematically is that for humans, people's rate of saying 6, that is, from the perspective of the other agent, starts at around 20% if the person looks to the right but is there. It's of course 0 when nobody's there. And if the person looks at the number, it goes to about 40%. If the person begins to reach for the number, it's about 50-55%. And we found that we get somewhat lower rates overall for robots. The rates begin to increase as you increase the human likeness of the robot. And they also show the signature that as the robot either looks at or reaches for the number, the rates also go up. So we see here indications of a mechanism being activated by the appearance of the robot, and more so as the robot becomes more human-like. The shocking thing is that the effect of the humanoid or the human-like appearance is so strong that even if you tell people, you show them an android like Erica, Ishiguro's Erica, and tell them this is a mannequin, the effect is still exactly the same. People don't have to make mind inferences. There seems to be an activation of a mechanism that sits deeper than that. Additional work we've done shows that it invites particular kinds of moral judgments if you show a robot that is either more machine-like or more humanoid, and here we didn't even go to android levels. And what we found is that in a text description of a robot or in this machine look, people distinguish in their moral judgments a robot and a human, and they, in a sense, lose that distinction when you show them a humanoid robot. I'm not going to go into the details. Some of you have read the original paper, and then there's a follow-up paper that shows this effect of appearance. The caveat here is, however, that not every study was able to replicate this effect, and we're now working on laying out, with some of the results that I'll show you, a more fine-grained scale, if you will, of human likeness and see whether the effect goes up. Maybe there's a curvilinearity, and that explains the lack of consistency in the results. Most of the time we get it. And the final one is really the one that I'm most interested in. I'm going to tell you about that. Appearance invites mind inferences. And there's one very recent nice study that shows across a full range of faces that are very machine-like, though they still have eyes, and you'll see that that's a key feature, through something that looks more like an alien, to be honest, to a human, and then there's sort of a morphing that happens in between. And what the authors asked people to do is, as they looked at a various array of these pictures, to ask whether this thing is alive, has a mind, feels pain. I don't remember what the hangs out formulation was. And has the capacity to converse. And what you see is that there's not anything going on until about this level, and then these ratings go up, and they all go up in parallel. So this is what it seems like. Oh, there's the sort of one mind dimension, and then there is this one human-like dimension, and they're related to each other. That's interesting. However, it's not so clear that this is really the way things look in the human mind and in its interaction with robots. First of all, a lot of the research, that block that I showed you, and also the selection that the previous slide showed, really is based on this diversity of robots that's unsystematic, where people claim that one thing is humanoid in one study and another one consider this more machine-like in another study. There's also no conception or conceptual analysis of human likeness. There are no defining features. There's no common metric that would allow you to translate studies or results from one study to the next. Here are 3 pictures of robots that all were called humanoid in different studies. And they differ in remarkable ways. They're all more humanoid than some kind of machine over here and less than Mr. Ishiguro's double. But nonetheless, we want something a little more systematic, something a little more sort of metrically comparable across studies. The side of mind inferences too, though there has been a bit more progress, also was limited by the fact that people sort of picked particular dimensions that they were interested in and then created some questionnaires, some more systematically, psychometrically supported than others. And there, on both sides, we thought we want to have a deeper analysis on figuring out whether there really is only one dimension of appearance, there's only one dimension of mind-likeness or having mind. And thus our goals were the following. On the appearance side, we wanted to gather a representative collection of robot images and really cover at least the robots that exist right now, analyze the physical appearance of these robots in a systematic and sort of fine-grained way. Now, the analysis you could do on a sort of engineering level. We were interested in the human perception thereof, and I'll tell you in a second how that worked out. And we also wanted to decompose this vague concept of human likeness into collections of features that might constitute this more vague concept. On the capacity inference side, we wanted to limit in some sense the domain or delineate it as social mental capacities. There are other things that you could measure and that are probably also important, could run into follow-up studies, but we wanted to focus on that, and I'll say a little more in a few minutes. You wanted to expand the previous item base and really see how many dimensions are there if you try to really cover a fuller range of social mental capacities, and construct a multidimensional measure that then would allow us to link the appearance side to the capacity side and examine which elements of appearance might invite which kinds of inferences on the social mental capacity side. So part one, decomposing appearance. And this is stuff that was reported last year at HRI, or last year, well, I guess it's this year? Yes, March 2018. We collected this large number of robot images of robots that exist right now or have existed for a while, or existed and maybe are not used anymore. We gathered 269 pictures from research, commercial. We solicited via email and listservs people to contribute these pictures. We then filtered them out such as that we don't have animals, we don't have duplicates of the same robot with different colors, and we also didn't accept low resolution pictures. Very few actually had to be removed for that, because the level of resolution wasn't particularly high, the threshold wasn't particularly high. That got us to 200, and then finally we edited the images in part to make the background uniform, like here for example, remove all the background, in part also to, if there were several versions, we selected a more neutral facial expression, and we preferred a forward pose rather than something to the side. And so these 200 robots, we had enough pictures to pick the best ones, selected those, and then created this both database but also an option to study the dimensionality of the appearance of these robots. And I have to sadly say that the ABAT database website is down. And I found this out this morning because I wanted to show you, oh, it looks cool, except it's down. I don't know what happened. Somebody didn't pay the site fee, and it was supposed to be transferred to the Brown server, and after 14 emails, nothing happened. I know this is totally unfamiliar to many of you. It'll be up at some point again. So the idea is to share these data and share the pictures with researchers to allow them to do sort of a more systematic way of studying human appearance. So what we do, we started with 29 features that have human labels that can be recognized, and reduced it to 19 features after pilot testing in order to figure out, are they really asking the same thing, or do we need a more sharp formulation? Is this impossible to judge? We got down to 19 and then developed definitions that really were mostly taken out of the Oxford English Dictionary, but applicable to robots. And then had a large number of participants basically make judgments about the appearance of a large number of robots. So here, for example, would be one of those items. Does this entity have one or more arms? Yes, no. And we also had foils, that is additional items that were clearly not in any way human-like, so machines, objects. I think there was a toaster in there, the famous toaster. And there were also a few people in there to set, in a sense, the scale and the judgment space. But the participants answered a subset of these robots, because 200 is a little bit of punishment towards participants. So each participant randomly was assigned to rate one feature in 50 robots, and each robot then was rated by 15 people on each feature. And that typically stabilizes the means or proportions in this case fairly well. So we had 200 robots and 19 features in total, over 1,000 participants, and they were taken crowdsourced from Amazon Mechanical Turk. That was before the slight disaster that seems to have happened with bots taking over and people participating in multiple ways with multiple Amazon Turk IDs, except that they all do it from the same GPS location, and you can actually start to identify them. But this was pretty good. Age range was good. Distribution was quite good. And what we then found is that, first of all, our average agreement, this is a form of kappa agreement among judges, was quite high. There were a couple that were in the 40s, 50s, some of them in the 80s, but overall we were fairly happy with the reliability, the inter-judge agreement. And then we calculated basically a percent of raters that endorsed a particular feature for a particular robot. That is the feature presence score, and that would look like for the features that we kept. We had grippers initially. Grippers were not reliable, and they were basically collapsed with hands. People weren't really good at separating grippers from hands. From fingers, I should say. And so they're now, for example, I'm just highlighting here a few things that you have also the fingers and legs, 100%. Everybody agrees among our participants, which is, by the way, not that frequent because sometimes people just give you pretty bad data, and it means you always have some variability, even in things that look very clear. And here's another one where the face is there but has no arms, and then here was Bina, who has eyebrows and hair and skin, and these are particular features that characterize these more android-looking robots. So this, you could keep going with 200, but then the question is, can you reduce this 200-dimensional space down to more basic dimensions where these features cluster together in ones that are highly correlated? And note that this is, of course, not an independent nature that we are studying here. It's the robots that exist right now. There are engineering constraints on combining features. There is probably a projection of human expectations about how to build robots, what they should look like. But this is the reality that we wanted to reduce. And what we basically did was a principal components analysis, or finding the eigenstructure of the 200 by 18 matrix, 200 robots, 18 features, and see whether these 18 features can be reduced to a smaller number of dimensions. And basically, you can then you hope that you have a more parsimonious description of human-like appearance with a smaller number of dimensions rather than having to give a feature map for each robot that has 18 of those features. And what we found was that it in fact reduces very nicely to 4 dimensions that cover 3/4 of the total variance. And this is pretty good for principal components analysis in general. And basically, we have body manipulators that hang together, hands, arms, torso, fingers, legs. We have facial features, face, eyes, head, mouth. And then very interestingly, we have surface features that really don't have much of a function, but that, in a sense, build up this android feel. Eyelashes, head hair, skin, being gendered. That doesn't mean that it is a particular gender. So it's not like female would be the feature in here, but rather that you can determine whether it's female or male. Has nose, eyebrows, or some apparel, clothes. And finally, mechanical locomotion is sort of the reverse. If you have a bunch of these other features, but then you have treads or tracks, then people reduce their judgment of a robot, or it appears of a robot being human-like. So these are the ones that really are positive features of human-like robots, and these are sort of subtractions. And what we then were able to do is for each robot, just to give you a few examples, create now a map where each of those 4 dimensions are covered by an average score, which is merely the score across the features that define this particular dimension. And you can find different robots with different profiles, and you can keep going in that respect. So this is a much more parsimonious way of identifying differences between robots. All right, so this is a pretty good start. And we can summarize the results of this first study that 18 physical appearance features, remember the gripper was removed from the 19 originally, can be reduced to 4 high-level dimensions. They very well represent the variance among the original 18 features in 75%. 4 subscales where we take the highest loading items for each of those 4 dimensions, create a simple scale of checking, say, 5 features, differentiate the 200 robots very well by their appearance profile. And it also means that we can now look at how these dimensions combine to an overall judgment of something that is human-like to different degrees. And that would then allow us to say, well, human likeness in the past was seen as a single dimension from low to high, but we now know how the appearance of a robot is constituted by these 4 basic dimensions. And we can ask, how did these dimensions contribute to an overall judgment of physical human likeness? So this is the goal of study 2, to decompose this vague concept into dimensions and features that we identified in study 1, to ask which ones drive the overall judgment of human likeness, and whether we can then predict from individual dimensions or individual features how human-like a robot will be perceived even if we didn't have the robot in this particular study. So we can then take any new robot and ask quick yes and no questions about the features and then make a prediction fairly, at least this was the goal, fairly good prediction whether this robot will be perceived as high or medium or low in human likeness as a combination of these dimensions or features. All right, so this is the measure that we used, very simple question again, and I want to say that we intentionally made these tasks very simple for our participants because we didn't want them to make complex judgments. We wanted to do something very simple for them, and we also wanted to be sure that they weren't invited to make comparisons or figure out what we wanted to do in the study. So we gave them basically a set of robots and asked how physically human-like does this entity look to you, and it was just a slider from not at all to just like a human. And we had, again, in our design, enough replication to stabilize the means. We had, in this case, 100 people, and with a pretty good age range. Each participant rated 50 robots, and we had, of course, only one variable to judge. Originally, we had 19 features. Now we have only one, human likeness, and we were able to get each robot to be rated by 25 people, and again, had very good inter-judge agreement on that. And the range of the human likeness scores really came out very nicely too, from 1.44, by the way, that was Jibo, all the way up to 96.46. That meant the scale was really used as a whole. People didn't sort of stay up too high or stay low too high. Our sample of robots that we gave people was really quite good as well. So now we can predict the single item human likeness judgment averaged across 25 people for each robot from the various dimensions that we have measured for each robot in the original study. So each robot had a particular score on each of these dimensions, and then we can run a simple linear regression. How well does the human likeness variability get predicted by the various dimensions that we measured here? So we see that surface feature uniquely explains 19% of the total variance. If you turn that into a correlation, it's 0.44. The body manipulators contribute an additional 28% of the variance of our human likeness judgments. 1.7 comes from mechanical locomotion, and you see, of course, it's a minus because it gets sort of subtracted. We have facial features, 0.5%, and these are unique variance contributions. That is, this is absolutely not overlapping with any of the other dimensions. But then there's also shared variance, and in fact, facial features and the surface features over here have a fair amount of shared variance. So it's not that facial features are irrelevant. It's that facial featured variability is in a sense confounded with some variability of the surface features, which is understandable because you can't really easily have eyebrows without having eyes. And that means the feature of having eyes can still be separately assessed. And we can say, well, under what circumstances does adding eyebrows do something over and above having eyes? And you'll see in a second that this actually does seem to happen. So overall, the prediction of our human likeness single item is 81% of the total variance explained. That's well over 90 in terms of a correlation coefficient. So we can basically decompose human likeness into relative contributions of these four dimensions, where really three of them, surface features, body manipulators, and facial features, are the strongest ones. And the mechanical locomotion really picks out a few robots that are unique in a way, in a sense, have a purely mechanical feature that subtracts from the human likeness impression. So this was pretty exciting. We were also looking at the specific individual features. I think statistically, the dimensional one is much better. It's parsimonious, but still people often ask, and it's a curious question. If you take these 18 features and ask, so how well do they do if you, in a sense, do a fine-grained analysis? It also means statistically you do overfitting. If you run the whole one, you can do resampling and do a discriminant, or you can do a cross-validation. Here I'm just going to show you the linear regression to give you a sense. Basically, if you take all these features and predict the human likeness scores for the robots, the correlation is 0.94. So again, it's above 80% of explained variance. And if you then ask, so which of these specific features are the winners. So you make them all compete and say, so which ones would I pick if I just had to do the best job possible? Which means you pick the ones that have both unique contributions that others don't make, but you also pick the ones that share a lot of predictive variance with others. They're sort of the strongest that combine unique and shared predictive variance, and it turns out that these three are the ones. These three alone correlate 0.89 with overall human likeness. And what happens really here is the torso gets you for sort of the first level. It's that body manipulator. It's the strongest element of body manipulator. Then skin and gendered are basically giving you the highest point. How much do you have of these android features? And then if those two sort of get averaged, then you have a moderate level of human likeness. And thus you cover the full range of our robots. So three features in principle. It doesn't mean psychologically they're the only ones that people pay attention to. It's just statistically they take their own contributions and their shared contributions with other features and turn this into a pretty high correlation. Yeah, David?
How strong are the intercorrelations between the features, either the 18 or the 4? I mean, do you have a lot of 0.7, 0.8 correlations between features or between the elements of the 4 subscales?
Yeah, so you basically have within each dimension very strong correlations among features, because that's exactly what you hope in a principal components analysis. You want to say this is a dimension that really is covered by a tight cluster of features, but the dimensions themselves are in the initial principal components analysis are completely orthogonal. They're completely uncorrelated. However, once you form the best 5 or so items, then surface features and facial features are correlated as dimensions at about 0.3, 0.35. Again, because it makes sense, there's sort of a physical, at least, if not logical, relation between them. But for the most part, they're fairly separate. But this is just sort of an exercise. If I had to just ask 3 questions, it's like a quiz, about your robot, then these are the ones that I would ask and could predict pretty well, of course cross-validated would be lower, what the human likeness score would be if we asked 25 people how human-like your robot is. All right, so even that with 3 items explains almost 80% of the variance. This is the thing that currently doesn't work, and it would be really cool if it worked. Namely, we basically have this linear regression sitting in the background based on our 200 robots, and you answer a survey, a few feature questions, and then we can put together a prediction how human-like your robot will be perceived. We'll find out. I'll make an announcement when it works again. Third part, now we wanted to look at the mental capacity side and also see what's the dimensionality of these mental capacities. So there was really this initial starting point that considered mind inferences as more or less one-dimensional structures, that you attribute more or less mind to a creature, to a machine. But a pretty influential paper from 2007, it was a single-page science publication by Heather Gray, Kurt Gray, and Daniel Wegner, proposed that there are really 2 dimensions to mind inferences, namely agency and experience. And then very recently, Kara Wiseman and colleagues from Stanford came up with a 3-dimensional solution that in a sense covers some of what Gray and Wegner found, but breaks up the agency dimension into 2 separate ones. And you'll see what we find is related to what they have. Those labels are a little weird, to be honest. The body one is sort of physiological, basic affect. The mind is a mix of all kinds of things, and the heart is emotions. And I'll make a brief comment on that a little later. But it was clear that if you add items that Gray and Wegner didn't use, they used only 18 items, then the dimensionality increases, which typically happens, but only up to a point. What we found as just sort of a punchline that there are 3 to 5 dimensions, and I explain this in a minute why, sometimes 3, sometimes 5. So one thing we noticed a few years ago was that if you look at all the items that Gray and Wegner used, there were some that really beautifully defined experience, such as hunger, fear, pain, pleasure, rage, and some that were beautifully defining agency, planning, emotion recognition, morality, memory, self-control. Now, footnote, this is a very heterogeneous set of items. It's like really weird. It's like, how does emotion recognition, morality hang together? Now, planning and self-control, you would say that's really prototypically agency. Memory is probably required for that, but that was a little weird. In addition, you see that these two nice clusters surround a sort of amorphous cluster of additional items that load on both of those dimensions. And these structures typically suggest there's a hidden dimension, you don't have enough items, you might even have heterogeneity here that if you added items, they would break apart. And that's really what motivated originally our approach to say, we don't think that there are only two dimensions. And that was before Wiseman published her paper. They basically beat us to it in some sense. But the results are not quite the same. So what we did in this new scale development was to expand the item pool to truly agentic ones, multiple items in each of these categories, about 5 of them. Bodily as part of that, affective, perceptual, cognitive, moral. And then iterate in multiple studies, multiple data sets, judgments of robots, humans, animals, various kinds of robots, in order to see whether these items hang together in particular dimensional structures in a way that would be relatively constant across different agents. And that was the strength of Gray, and Wegner, that they really had, I think, 15 different agents and showed that in a two-dimensional space of agency experience, you can place them from God to a dead person, from an infant to a human with brain damage. So that was in a sense the strength. The methodology was a little strange, but this was definitely a very influential first step. And what we then found initially was that over the several studies, I think 5 or 6 studies, there was a convergence on 3 dimensions. And what convergence means is that there's a set of items that keeps hanging together. And even if you add new items or you take some of those items out, this component or this dimension keeps showing up as distinct from other components and dimensions. And basically what we found was something like affective physiological, which is very similar to the experience dimension from Gray and Wegner, and partially the body dimension of Wiseman and colleagues, a social, cognitive, and moral one, where you see now emotion recognition and morality that was collapsed into agency in Gray and Wegner really comes out as a separate dimension. And the final one, very interesting, reality interaction. And what's cool about this one is that this dimension isn't just sort of one big capacity, but it's a process, and you'll see in the form of the items, a process by which a reasonably intelligent agent engages with the environment. The items will make that clear. But then we also found in a couple of our data sets that there weren't just 3 dimensions, there were actually 5 dimensions. And basically what the difference was is that when we asked people to infer what capacities a robot, an animal, a human, whatever agent had, you found a 3-dimensional structure of the affective, the social moral, and the reality interaction. And you see here the process, moving on your own, learning from instructions, seeing and hearing the world, communicating verbally. This whole process is first perception, then you move on your own. You learn either from instruction, and there are other learning items too that would load, but they're not quite as well loading as these here. And then you communicate verbally. Now you don't have to have all of these features, but the more of them you have, the stronger your score on this particular dimension. You see here also the alphas, which are a degree to which the items hang together, so that goes back to David's question. They are very well correlated. And the reason why there are double as many as here is because underlying the first 2 is actually this 5-dimensional space where affect falls into positive and negative when we ask people, what capacities would you like a robot to have? And what happens here is that positive and negative, also in human emotion research, typically are not negatively correlated, but rather they're orthogonal to each other. You could have both positive and negative affect. You could have a little of each. And in this case, what happens is that people really liked, or reasonably liked, positive affect in a robot, and absolutely didn't like negative affect in a robot. And thus, these items came apart into 2 separate dimensions. And the social moral also came apart into a more uniquely moral one, disapproving, telling right from wrong, upholding values, praising moral actions, and more sort of classically social cognition, inferring what a person is thinking, planning for the future, understanding others' minds, and setting goals. And what's cool about that too is these are social cognitive in the sense that as you infer other people's minds, that informs how you plan and how you set your goals in a social world. And then finally, the reality interaction, which of course doesn't change. So when you ask people a question that in a sense elicits their images of robots in the future and what they would like or don't like, there's a 5-dimensional structure in their representations. If you ask them what they have encountered so far in movies and in pictures and news and so on, then it's a 3-dimensional structure, but they nicely hang together in a sort of a hierarchical way. All right, fourth and final point, now we want to relate the appearance features, the 4-dimensional space there, or in fact the 3-dimensional space, leaving out for convenience and because it contributes so little, the mechanical motion, the tracks and treads, and relating that to mental capacities. And basically what we're asking excuse me, here is if you are exposed to robots of various appearance features, what do you infer about their mental capacities? Now, of course, this is guesswork, and in the worst case, it's sort of all random and people don't very much agree on it, or they all say, I don't know, and they are in the middle of the scale. Or it could be that people have actually fairly strong intuitions. And if they do, then we should be able to show that they agree on these intuitions and that the intuitions can be systematically predicted from appearance. And we thought it's probably going to be somewhere in between. So what did we use as methods? We selected representative robots, and I'll show you in a second how we reduced it down from 200 to a set of 24, and then asked people to make inferences about a single robot on 24 items that captured these 3/5 dimensions of social mental capacity. And because we gave them only one robot, they had no comparison. They didn't really know exactly what the study was about. They had one robot somewhere on the human likeness scale, somewhere in the space of 4-dimensional or 3-dimensional appearance components. And that's important because we don't want people to guess that we are interested in human-like appearance or any of these things. So they make these judgments. It's a fairly fast task for them. And they come out nicely, again, as the principal component. What you see here is a 3-dimensional representation of the body manipulator dimension, the facial feature dimension, and the surface look dimension. And this is the result of a cluster analysis that basically finds, in this case, robots that hang together. So principal components analysis is about items hanging together. Here, about robots with a particular location in the 3-dimensional space, finding the ones that in a sense bump against each other and hang together like a little social group. And you see them here colored from 1 to 7. Down here it's basically nothing of any. It's like a complete machine. Then you see the light blue, you get increases in facial features. Then you see it gets towards the yellow when you also have body manipulators added. And then the final step is really to add the surface features all the way up to the androids. And the few out here are ones that have surface features but don't have body manipulators. And those are the sort of desktop hats, heads like Fur Hat or Bina and similar ones. So these are very nice clusters coming apart. And we basically then selected a subset from each cluster and created a total of 24 robots that represented the space. And because human likeness basically goes from here upward to having none of it to having all of it in this dimensional space, we represented human likeness, but not as a single dimension, but as a recombination of the 3 underlying dimensions. All right, so the overall human likeness score was predicted, Yes. The overall human likeness score had a relatively powerful predictive effect such that if I look at the human likeness score from the previous study, study 2, which a bunch of people assigned to each robot, and then I take the average rating that people gave us in this third study on the affect subscale, the social moral subscale, and the reality interaction subscale, then we have a fairly nice linear prediction for each of the subscales You also see the main effect, the intercept of the regression lines here suggest that people, of course, attribute much more strongly the capacity for reality interaction to whichever of the 24 robots they rated, and very little of the affective capacities. But as the robots begin to look more and more human-like, now as a single dimension, this even low affect dimension begins to climb up. And the social moral is in the middle and climbs up, and the reality interaction starts higher and climbs up. So this is pretty good. This is breaking up the capacity side into 3 dimensions, but keeping the human likeness as a single dimension. But as you know, we believe that the human likeness is actually itself a multidimensional space. So what we then did basically was looking at all the features on the capacity side and all the features on the appearance side, and just plotted them together in a big matrix as a heat map, basically, to see whether there are actually groups of relationships. And it came out quite nicely. The lighter one towards the yellow is higher and higher correlations. So these are linear Pearson correlations. And towards the dark blue means it's 0. And on the left, we just simply ordered the positive and negative affect, the social and moral items, and the reality interaction items. And down here, we sort all our appearance items into the groups of surface features, body manipulators, and face. And you see that certain groups of items don't correlate with certain dimensions on the capacity side, and others correlate very well. And this is just on the feature by feature basis. And here you see that the features are not just related to each other, but the feature bundles are related to other to other capacity bundles. So this was the overall first shot, but then we took our dimension scores, which are averages over here and averages over each of our subscales here, and did again some linear regressions, checked for curvilinearity, and there wasn't really much, so we were safe to do standard regression. And I'm going to show you first the 3 human-like appearance dimensions, mental capacity dimensions in the 3-dimensional space, and I'm going to show you the correlations that each of these dimensions has with each other one. First, ignoring any intercorrelations among the dimensions. There are not many, but we just keep them in for now. And you see the darker the shading, the higher the correlation. So affect inferences. I get one robot and I say how much I think that robot might feel pain, might have some affect, might be hungry, might feel pleasure. And again, mostly people say not much at all. But to the extent that it has facial features, that correlation jumps up to 0.7. And to the extent that it has a surface look, it jumps up through a correlation of 0.6. Social moral capacities are also inferable from these 2 dimensions, surface look and facial features. And reality interaction, and this is maybe the least surprising, is very well predicted by having torso, legs, arms that actually allow you to manipulate reality. But it also has a little bit on the facial feature side, something like eyes and other sensors. So this is a pretty good start. And now you look at the regression coefficients, which is basically the relationship between each dimension and the other dimension, holding constant, statistically controlling for the relationship with other dimensions. And you still get a very nice picture here. The facial features really seem to determine or predict the affect ratings. Social moral mainly also by facial features, and body manipulators most strongly predict reality interaction ratings. So that's the 3-dimensional space. But then we wanted to look at the 5 dimensions where social moral breaks into 2 and positive negative affect breaks into 2. And that's what we did next. So now everything stays the same down here, but on the y-axis we basically have, for each of our 5 capacity dimensions, the relationships with each of our facial feature of our appearance feature dimensions. And what we see here is that both positive and affect show the same pattern. So even when you break them up, basically means the same. If you have a high degree of facial features and or surface look, that means people will give a very strong rating, or relatively strong, from 0 up for this robot's affective capacities. Social and moral actually nicely come apart now. It's the moral ones that really seem to be predicted by surface look and facial features. Social cognitive capacities don't have any particular feature that seem to reveal them. People don't respond with strong inferences of social cognitive capacities to any one of these dimensions. And this is, of course, just a replication from before because this isn't change. We didn't break up anything here. So these are the Pearson correlations, and these are now the regression coefficients. And you see here again that it's facial features that actually do more of the job, although the surface look contributes a little. And remember, facial features and surface look are really correlated. But it seems that the basic element of having eyes, face, and a few other features seems to do most of the work of driving people's inferences. The surface look is a little more dress up, but it doesn't strongly additionally change people's inferences about capacities. And we see again that the moral one is really the one that's driven by the facial features and not much at all the social one and reality interaction again over here. And these are very strong correlations. If you're in psychology and you get correlations in the 40s to 60s, that's pretty amazing. Now I have to give one caveat here. These are correlations across 24 robots. Because each person only rated one robot, you can't run correlations with people as your replications. You have to run it as robots. So I take the average people scores of how much they inferred about each of their own robot, and then correlate these distributions of the 24 robots with the appearance dimensions that we got from the previous studies. That means you correlate aggregated scores. And whenever you aggregate, you basically get rid of some error variance, some random variation. And that improves correlations. It doesn't mean that this is a confound or that's a problem. It's just a cleaner measure of what the community thinks this robot might have as its capacities. But that in part explains why the correlations are so much higher than what you would see in other studies. All right. Finally, we did a multiple regression. Rather than doing these maps of correlations, and the regression coefficient weights, of course, that you already saw are what's underlying here. And we can ask, how well are inferences about positive, negative affect, social capacities, moral capacities, and reality interaction capacities predicted merely by appearance features of the robot? People just see one robot at a time, and we look at how the combination of these features, in a sense, seems to determine or influence what capacities they see in this robot. In a one-shot, simple first impression. No interaction yet, not even a dynamic video, just the look of it. And that was the whole point. Does the look have any impact? And it has a powerful impact such that each of these dimensions, positive, negative affect, moral, and reality interaction that we saw earlier, is very well explained. Just around about half of its variability is explained or is predicted by appearance. And the only one, the social cognitive capacities, doesn't seem to be explained. People don't seem to have a strong intuition that robots of different appearance have different social cognitive capacities, social skills, if you will. So these are pretty powerful results that should really make us realize that appearance features we put on robot don't just have sort of these interesting intelligence and other maybe sociability consequences in terms of the inference space that people have, but actually directly seem to determine capacity inferences, which means I have the expectation that the robot will be able to do certain things, will be good at certain things, will have certain skills. And then of course that means if it doesn't have those, it just has facial features and surface features, but doesn't really have any of these moral or affect capacities. That might be quite a bit of disappointment, surprise, shock, maybe rejection of the robot, and so on. So as many probably argue nowadays, we have to be very, very cautious in putting these human-like appearance features on robots. So conclusions, robot appearance is not a unidimensional, but a multidimensional construct. We looked at 18. You could have somewhat more, but I think they will all collapse into the same four-dimensional space. 18 collapsed down to 4, where 1 is really sort of more capturing the mechanical subtraction. Human-like appearance is largely constituted by these dimensions. So if you ask people an overall judgment of human-like appearance, that really can be predicted very well by combinations of these underlying appearance dimensions. And on the capacity side, social mental capacities are multidimensional. I say obvious because it was a very unlikely hypothesis that there's just one dimension of having more or less mind, although people did in some past studies actually say that or try to study that. But it's obviously multidimensional, and it turns out to be 3 to 5-dimensional, depending on whether you ask a more detailed question about either wanting the robot a certain way or thinking what the robot's capacities are. And even if they are highly correlated, social, moral, and positive, negative affect, you can then ask what their individual what the individual impact of appearance features is on these capacity dimensions. And social and moral then come apart, whereas affect stays together. So we have this further differentiation. And clearly appearance has a powerful impact, but it isn't just like appearance overall, one dimension, has a powerful impact on what mind people infer, but we can make much more detailed, dimensional, specific predictions about which features that you put on a robot will have what impact on human likeness, overall ratings, and on specific inferences about the robot's capacities. And that's sort of the picture, it's the new look, if you will, of the big topic of appearance in HRI.